This is Sanvita from Department of Civil. Today I am here to explain the influence of gravity. The influence of gravity, exploring the fundamental force that shapes our universe from falling apples to orbiting galaxies. So basically, what is gravity? Gravity is one of the four fundamental forces of nature, responsible for the attraction between objects with mass. The first described mathematically by Isaac Newton in 1687 and later refined by Albert Einstein's theory of general relativity. So gravity governs and later everything from the motion of planets to behavior of light near massive objects. So unlike other fundamental forces, gravity is always attractive and acts over infinite distances. Through its strength decreases with the square of the distance between objects. So this inverse square relationship means that doubling the distance reduces gravitational force to one quarter its original strength. So Newton's law of universal gravitation. So Newton's revolutionary insight was that the same force pulling an apple to the ground also keeps the moon in orbit around Earth. His law says that every particle attracts every other particle with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Here F is equals to G m1 m2 by r2 where F is the gravitational force, the attractive force between two objects, which is especially measured in newtons. And G here is the gravitational constant, which is 6.674 into 10 to the power of minus 11 Newton meter per kg whole square. But this is a universal constant of nature. And M1, M2 are the masses of the two objects in kgs. And R is the distance between the centers of the two objects in meters. Gravity on Earth. So on Earth's surface, gravity accelerates all objects at approximately 9.8 meter per second square, regardless of their mass. So this acceleration, denoted as g, means that in the absence of air resistance, a feather and a hammer would fall at exactly the same rate. A principle famously demonstrated by Apollo 15 astronaut David Scott on the moon. So 9.8 is meter per second square acceleration, which is a standard gravitational acceleration at Earth's surface, and 5.97 into 10 to the power of 24 kg mass, total mass of the Earth, and 6,371 is the kilometer radius, average radius from Earth's center to the surface. So Earth's gravity varies slightly depending on location due to factors like altitude, latitude, and local geology. At higher elevations, gravity is slightly weaker because you are farther from the Earth's center. Similarly, at the equator, centrifugal force from the Earth's rotation slightly reduces the effective gravitational pull. The Einstein's revolutionary view is a general relativity. In 1915, Albert Einstein transformed our understanding of gravity through his general theory of relativity. So rather than viewing gravity as a force acting at a distance, Einstein proposed that massive objects actually curve the fabric of space-time itself. So imagine space-time as a stretched rubber sheet. When you place a heavy ball on it, the sheet curves around the ball. So smaller objects nearby naturally roll toward the depression, not because of a mysterious attractive force, but because they are following the curved geometry of the sheet. So this is how gravity works according to Einstein. So gravity is influenced across scales. So gravity operates at every scale in the universe, from the quantum realm to cosmic structures spanning billions of light years in its shapes the behavior of matter and energy throughout the existence. So microscopic scale. At atomic scales, gravity is the weakest force. Electromagnetic and nuclear forces dominate. A single proton's gravitational attraction to another is 10 power 36 times weaker than the electromagnetic repulsion. The human scale, gravity keeps us grounded, determines our weight, and influences everything from how we build structures to how blood flows through our bodies. So it's the constant companion of everyday life. Planetary scale. Gravity shapes planets into spheres, creates atmospheres, generates tides through the moon's pull, and determines orbital mechanics. It's why Earth orbits the Sun at precisely the right distance for liquid water. And coming to cosmic scale, gravity binds stars into galaxies, galaxies into clusters, and drives the large-scale structures of the universe. It powers stellar fusion. creates black holes and architecture's cosmic evolution. So this is about the microscopic scale, human scale, planetary scale, and the cosmic scale. Moving on, orbital mechanics, dancing with gravity. So an orbit represents a delicate balance between gravity and inertia. So when an object moves fast enough horizontally, Earth's surface curves away beneath it at the same rate gravity pulls it down. The object continuously falls toward Earth but never reaches it. This is what we can call an orbit. Low Earth orbit is LEO, which is of 160 to 2000 kilometer altitude, and speed is about approximately 7.8 kilometer per second, and period it takes about 90 to 120 minutes. It is the home to the ISS and most satellites. Coming to geostationary orbit, GEO, it is about 35,786 kilometer altitude, and speed is about 7.07 kilometer per second, and period is of 24 hours. Satellites appear stationarily above Earth, perfect for communications. And then escape velocity. So 11.2 kilometers per second from Earth's surface reach the speed and gravity can no longer pull you back. You are free to explore the solar system. Tides. The moon's gravitational dance. The tides demonstrate gravity's influence in our daily lives. The moon's gravitational pull creates a bulge in Earth's oceans on the side facing it. Surprisingly, another bulge forms on the opposite side, not because the moon pulls water there, but because the moon pulls Earth itself slightly away from the water. As Earth rotates through these bulges, most coastal areas experience two high tides and two low tides each day. The sun also influences tides, though which about half the moon's effect due to its greater distance. There are two types of tides, spring tides and neap tides. Spring tides, during a new and full moons, when the sun, moon, and earth align, their combined gravitational pull creates the highest high tides and lowest low tides. And neap tides, during quarter moons, when the sun and the moon form a right angle with earth, their gravitational forces partially cancel, producing smaller tidal ranges. So there are two ways of looking at gravity. Uh, the first one is Newton's law of universal gravitation as a force. So this is a classic theory which is developed by Sir Isaac Newton in the 17th century. It describes gravity as an attractive force that acts instantly between any two masses, the attraction, mass, and distance. So this model works extremely well for most everyday calculations like determining an object's weight or planning space missions. So key takeaway is that Newton saw gravity as an invisible instantaneous force pulling objects together, where F is equals to G into M1 into by R square. And the second way of looking at gravity is that Einstein's general relativity as a wrapping of space-time. So Albert Einstein's theory of general relativity in 1915 is the most accurate description of gravity in modern physics, especially for very massive objects like black holes or for the entire universe. Here he explains about the space-time, curvature, and the motion. So moving on, extreme gravity is about black holes. The black holes represents gravity's ultimate trump. When a massive star collapses, it can compress so much mass into such a small piece that gravity becomes overwhelming. At the event horizon, the point of no return, even light cannot escape. So gravitational collapse. Stars about 25 solar masses can collapse into black holes with their nuclear fuel is exhausted. So gravity crushes matter to infinite density at the singularity. And then time dilation. So near a black hole, time slows dramatically relative to distant observers. At the event horizon, time appears to stop completely from an outside perspective. And spaghettification. The difference in gravitational pull between your head and the feet near a black hole would stretch you into a long, thin strand, a process physics actually called spaghettification. The future of gravitational physics is that despite centuries of study, gravity remains mysterious. So modern physicists continue to probe its secrets, from detecting gravitational waves to stretching for a quantum theory of gravity. Gravitational waves. Ripples in spacetime caused by accelerating masses first detected in 2015. So these waves let us fear cosmic events like colliding black holes, opening a new window on universe. Quantum gravity, the holy grail of physics, unifying quantum mechanics with general relativity. String theory and loop quantum gravity are leading candidates for this theory of everything. And dark matter and energy. Observations suggest 95% of the universe consists of the mysterious dark matter and dark energy. Known only through their gravitational effects, understanding them could revolutionize physics. So gravity continues to captivate physicists and shape our understanding of reality. From keeping our feet on the ground to stretching the cosmos, it remains one of the nature's most profound and beautiful phenomena. Thank you.